We're into Unit 2, Periodicity, all about the periodic table and the trends in the periodic table. This will be much of what you're going to see in the learning objectives will be review from last year, first year chemistry, plus 2 new topics, photoelectron spectroscopy, using technology, integrating technology into more evidence to show for some of these trends that we see in the periodic table. And then there's another one called mass spectrophotometer or spectroscopy, both of which are technology integrated into providing more evidence to what we see as far as the trends on the periodic table. Please make sure you go through this line by line. This is a good review even at the end of a unit as well. So please make sure you really see the essential of what you're trying to learn through this unit. How we've learned about the periodic table and the elements on the periodic table and some of the characteristics, physical and chemical characteristics that they have is through studying light. And light is made up of a wave. And waves have either a certain amount of wavelength or a certain amount of frequency that comes with it. And so here we have two equations that you're familiar with. The use of these two equations helps us to be able to identify what type of radiation we're looking at, what type of wavelength of that radiation, as well as its frequency. So before we go into the calculations using either the speed of light equation or the energy equation, we're really going to go into, we're going to understand what each of these different types of radiation, what it does to particles. For instance, when you go and put your food in your microwave, what you're really doing is you're exciting, you're really moving and rotating the particles, the water molecules that's in the food. Thus, it's causing the particles to heat up and emit heat. And that's molecular rotation in a microwave. But then when you apply infrared to substances, what you're really doing is you're vibrating. You're causing those particles to vibrate, not rotate, but vibrate. And that's the movement out, in and outside three-dimensionally. And then when you apply visible light as well as ultraviolet, what you're really doing is you're exciting the valence electrons. And so you're causing electrons to transition within the atoms of different substances out towards an excitation state, and then of course return back to the ground state, emitting light and or heat. Now when you get to, so this is for the visible and ultraviolet, you're really seeing electrons transition, the valence electrons transition when you're applying these two forms of radiation. When you get to higher than that, X-rays, you're really moving core electrons, which are not the outer valence electrons like you're seeing here. You're moving core electrons when you apply X-rays. But then also when you get to gamma rays, you're actually you're moving nuclear parts of the atom, which is the protons and the neutrons inside the nucleus. So that there you're going to need a lot of energy in order to change up the core, the nuclear core of an atom. But we're only seeing these four different these four different types of radiation and what it does to those particles when you're doing that. So let's go ahead and calculate now. Calculate using the speed of light equation or the energy equation. I'm going to do just a few examples, and the answer key is down the bottom, of course, but we're going to use this as a way to help us to just review how to calculate. So here in the first example, we've got a light that has a wavelength of 97.3 nanometers. Now, the speed of light is in meters per second, so we want to convert our nanometers to meters when we're using this equation. So in converting that, and I'll just do one that shows that conversion, you're taking 97.3 nanometers and you're converting it to meters. So 10 to the 9th nanometers is in 1 meter. And so when you convert that, I get 9.73 times 10 to the negative eighth as my um, wavelength in meters. So this is my wavelength in meters. Notice things cancel out. Once again, this is my wavelength. So then I plug it into my equation up here, my speed of light equation. I've got my speed of light, which is this constant, 3.00 times 10 to the eighth. I've got my wavelength in meters, which is what I want. I can solve for frequency by just substituting into this equation. I don't have much room, but I'm just going to squeeze as much as I can. So I'm going to plug in the speed of light, and then I'm going to put the wavelength in, and I'm solving for frequency. So upon solving for frequency and dividing my numbers, I get an answer of 3.08 times 10 to the 15th power. Now, to calculate the energy, all I'm going to do is substitute my frequency in and multiply it times Planck's constant, which is h here, and it's this small number, and then that will give me the energy of my light. So I'm going to work my way over here on this side. E equals, it's Planck's constant, and then multiplied times your frequency, which we found was 3.08 times 10 to the 15th power. So multiply those two and you will get 2.06 or 4 times 10 to the negative 18th. And this is in joules. So I put that number in. So practice these problems, work through each one, pause, and make sure you understand how to calculate using these two equations, okay? And check your answers, of course. All right, you should study these definitions as you had done last year as a way to understand how to apply them to the periodic table and the trends in the periodic table. I'll brush over really fast, however, make sure you read it carefully, okay? If you look at the atomic radius, the radius is actually decreasing along the period, which means along the rows on the periodic table. So it's decreasing going from left to right and then increasing as you go down. And we'll talk about why it's increasing and decreasing based on Coulombs Law. Ionic radius, it really depends on what we're looking at oftentimes, so it really is important that we look at equivalent things like isoelectronic ions. Oftentimes, isoelectronic ions will increase going across from left to right because there's more protons, increasing the Zeph, the nuclear charge. And then going downward, you're also seeing an increase in ionic radius because of the energy level increase. Ionization energy. Now, there's the first ionization energy, second and third ionization energy. The first one is always the removal of the first valence electron. And then as you further move into the inner shell electrons, you're seeing greater ionization energy, of course, because it's closer to the core, the nucleus here. But ultimately, you see first ionization, then you move further in, second, third, and then fourth would be the next level down. As you remove an electron, we oftentimes apply that energy to an atom, and when applying that energy to the atom, you see the atom no longer become an atom, it's a cation because it's lost an electron. So this is the lost electron right here that is fallen or removed from this atom right here, X. Now, second ionization would be the removal from X. After you remove the first electron, now you formed X plus. Now you're applying energy to remove another electron. Upon doing so, now the second electron is removed, leaving you with X2 plus. And then so on and so forth. The third one would just produce X3 plus, removing the third. So here's your first electron, second electron, and third. So ionization energy is basically this, whatever ionization energy you're on, the third one for instance, would be the sum of both the first and second ionization energy. Okay? So ionization energy generally increases going across the period as well as and decreases going down. Electron affinity is basically the energy change when an atom gains an electron from an atom in the gaseous state to form an anion. So it is the opposite of ionization energy. So here you have an atom in its gaseous state. You add an electron. Now that atom becomes an ion with a negative. This is very difficult to see, but I'm going to emphasize that it is a negative charge that atom becomes as a result. Okay, so it is a -1 charge. And of course, energy is released as a result, and that energy release is called electron affinity. And now, electron affinity increases going across the period and then decreases going downward. And then electronegativity is the ability of an atom to attract electrons towards itself in a chemical bond. Specifically, it's for bonding. So the highest reference, or the reference for the highest electronegativity is fluorine. And generally, electronegativity increases going across the period and decreases going down. Now, I know it's so easy to try to memorize based on what you're seeing here, but you really do have to always explain your reasoning behind your understanding of the trends. And so please make sure you don't make an effort to try to memorize this. You really understand Coulombs Law and how all of these physical and chemical properties play out in Coulombs Law. So really, if you understand Coulombs Law, you won't have any trouble understanding how to see or be able to answer any of these questions when it comes to trends. Okay. Electron configuration. This is just a review of electron configuration. Hopefully you can go back, if you need to go back to videos and such, old videos, YouTube videos, to understand where these orbitals are located, the S, the P, and the D, and the F. And where the 1s specifically is located on the periodic table. Please make sure you go back and review. But if you look at your periodic table, you'll notice that if you have the 1s with 2 electrons in it, the two electrons in the 2s, 6 electrons in the 2p, and 1 electron in the 3s, you are about at the location of sodium. So the element name is sodium and the element symbol is Na. So you're really practicing your element symbols and names because the periodic table that you currently are using for AP doesn't have the name. So please practice that. B, we'll just do a few. Again, the answer key is below so you can check your answers as well. So here we have all the way to the 4s. These are all ground state, by the way. They're not excited state electrons. So you're going all the way to the 4s, looking at my periodic table and yours. It should be calcium. 4s is where calcium is located, 4s2. And the element symbol is Ca. So you can go through each of these and make sure you understand that. What is the maximum number of electrons in each of the following subshells? It is a review. For the 2s, it is 2 electrons, and you can figure out what happens for the other ones as well. Max, by the way, you're looking for the maximum electrons. Write the noble gas configuration for the following elements. So I'm looking at phosphorus as the first example. I find it on the periodic table, and the noble gas that comes right before it is neon. So I'm going to use this as a shorthand for phosphorus's configuration. And so after that is the 3s2 and the 3p3. So this is the noble gas configuration. I can do deuterium as well. Why? Deuterium, the noble gas that comes right before deuterium is krypton. Following that are the, let's see, the 5s2 and the 4d1. So this is deuterium's noble gas notation. Go ahead and work through the rest. And then for the fourth question, it's asking for the electron configuration for the valence electron of each of these elements. So I really am not going to be worried about the inner shell electrons. I'm looking at only the valence. So for bromine, the valence electrons are located on the 4s, so it's 4s2 and 4p5. So that's why bromine has 7 valence electrons. And we're really focused on the valence electrons because that's where the bonding takes place. You can do the rest and work through. Draw the electron dot diagrams, which is also called the orbital electron box diagram, which is also called the orbital notation for each of the following. I'll do titanium, and then you can go ahead and work through nitrogen, okay? So titanium, I don't have much room down here, so I'm going to go ahead and do titanium on the side right here, if you don't mind. So I'm doing question 5A, titanium. And so to do the orbital notation, all you're doing is writing out all the configurations, the orbitals. So we start off with the 1s, then comes the 2s, 2p, 3s, 3p, 4s, and then the last one is the 3d. So there are 5 lines for the 3d. So for titanium, we're filling in 22 electrons. So this is my way to check to see how many electrons. And I'm always going to fill the lowest energy level first. And I'm going to follow some of my rules, Hund's rule here, where I'm going to stack the electrons singly, then doubly. Now, if no one's watching, you can just double it up, but on the last orbital, you must go singly and then doubly. And then titanium is only second spot on the d orbital, so in the 3d orbital. So here are your 2 electrons for titanium in the 3d orbital. So that is the orbital notation. Now we're going to do configurations for ions, and the ion that you're looking at first is phosphide ion. Now, how do I know this is phosphide versus phosphorus? Is the charge, the minus 3 charge that you see, or the 3 minus charge? You could write it one way or the other. And oftentimes these common ions occur because the atoms are better off filling their outer shell. And how they fill their outer shell is to either gain electrons or lose electrons. So phosphorus likes to become phosphide with a 3 minus charge. To write the configuration for phosphide is, and I'll just do the top, is to see that when phosphorus gains 3 electrons, it's isoelectronic with argon. So argon's configuration looks like this. 1s2, 2s2, 2p6, 3s2, and 3p6. And oftentimes your common ions are going to want to have either to be isoelectronic with the noble gas or to have this a pseudo noble gas configuration. And when I say pseudo, it means fake. So it's going to have a fake noble gas configuration, and metals tend to do that because they have this d orbital that doesn't quite let them doesn't quite let them be isoelectronic with the noble gas. So the best bet is to be to have a pseudo noble gas configuration. Let's go ahead and do B to see the pseudo noble gas configuration. So nickel normally has 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8. So 2 plus means it loses 2 electrons, and the first thing you want to do is oftentimes, not always, but more often than not, you lose the valence electron, which is the 4s. It's on the outermost shell. So essentially, your configuration ends up, when you clean it up, being 3p6 and 3d8. Okay, so clean it up a little bit. And that is your final configuration for nickel 2 plus ion. Now let's look at the next problem. Number 7, what element is in the electron box diagram below? So it looks like we're looking for an element that goes all the way to 3p4. It's kind of hard to see. Hopefully I realigned it for you. 3p4. So on the periodic table I look for 3p4 and I see that it's sulfur. So the answer is sulfur. Go ahead and work through this next problem. You've already been given the definitions for ionization energy and radii, and you have a sense of what to do. I would like for you to try this problem out in light of Coulombs Law. So I want you to think of these two ideas in Coulombs Law. Force as it relates to charge, and force as it relates to distance. We know that charge is about Zeph. So if you use Zeph in your explanation, you will be in a good place when you're talking about charge, core charge. And then when you're talking about distance with relationship inversely related to force, that is, you really want to talk about the energy levels that these particles have. So n equals 1, n equals 2, the first, second energy levels. So it really is going to be a discussion between distance with respect to force or charge with respect to force. So try at it and see if you can recall Coulombs Law and the definitions that we covered on the second page of your notes with respect to ionization energy and ionic or atomic radii. Go ahead and work through FRQ number 2. Much of what you're going to do as you go through these FRQs is to learn how to explain it well and to explain it thoroughly and to give evidence and reasoning for your explanation. So it's your QSIRs, your SIRs basically, when you were working through it all last year. So in your explanation, one of my pet peeves is to make sure you don't use the word it. Use the element or the ion in place. So instead of saying calcium, or instead of saying it, say calcium, Ca. You can actually use the element symbol because they are standardized on the periodic table. In explaining all of these questions, the root of most if all your explanations is Coulombs Law. So let's informally cover Coulombs Law right here. F equals, force equals K constant, charge of both particles, Q1 and Q2, and then distance squared. So this is Coulombs Law. You're applying Coulombs Law. You're not calculating Coulombs Law. You're actually understanding that as charge goes up, Coulombic force increases. As distance increases, Coulombic force decreases. So you're seeing a direct relationship between charge and force, an inverse or indirect relationship between distance and force. So that should help you to be able to go through your explanation. Please do not read the answer before you do the explanation. You're working on your ability to explain thoroughly. And when you explain, please make sure you use your evidence. What are some evidence for charge? It's the Zeph calculation. What are some evidence for distance? It's your energy levels. Energy level 1, 2, 3, etc. So please make sure you're working on your explanation, not looking at the answer and then explaining, making sure you're doing the explanation and then looking at the answer to see what you can fill in as far as what you're missing from your response. So this section is on the topic of photoelectron spectroscopy, and this is very much run like a POGL in essence. So it's building your learning as you go through this part of the worksheet or the notes. So it starts off asking, what is ionization energy? And if you recall ionization energy, hopefully you can answer this before I write it down myself, but it's the energy to remove an electron. Now, there's first, second, third ionization energy. Why are we learning about photoelectron spectroscopy? It's also called PES. We're learning about PES because PES is actually how we get the data for ionization energy. Like when you're given first ionization energy being 20 kilojoules per mole, you're actually getting that data from the instrument called a photoelectron spectrophotometer. We can measure ionization energy of a valence electron by bombarding atoms with fast-moving electrons in a technique called photoelectron spectroscopy, PES. In PES, we get the information all about the energy levels when we get information about all the energy levels when a photon knocks an electron out of an atom. We use very high energy photons. In PES, we use very high energy photons, which have, and if you recall, the high energy photons are the ones that have the shorter wavelength. Which types of radiation, the top two highest, on the electromagnetic spectrum would that be? And if you remember, gamma being the highest, gamma rays, and then up next is your X-rays. So these are the two types of radiation they use to basically bombard those the atoms that we're trying to measure. Go ahead and press pause and read this little section. We will review it as we go over the spectrum itself. Now, the way we go about finding the ionization energy is, as we stated up here, we bombard the atom with fast-moving photons. And that photon has energy involved in it. And so we actually measure the kinetic energy of the atom that we're bombarding before and after. And of course, that becomes interpreted in what is called ionization energy. The output of that data is in this PES right here, this spectrum right here. And you'll see that removing an electron that is in the core, like this, the 1s electrons are usually closer to the nucleus, is going to require more energy. And then as we move out further in terms of the valence shell, like this, for phosphorus, it's the 3s and the 3p, you're seeing less energy required to remove those electrons. And of course, 2p electrons and 2s are in the middle. So this graph looks counterintuitive, but the way you read it is higher energy on the left and then lower energy on the right. This must be the valence shell electrons, and that this must be the inner shell electrons moving that way because it's higher energy. The number of electrons can be seen on the y-axis right here. And so if you see this first peak being 1s, you know there's 2 electrons in this. That's why the 2s and the 3s have the same peak height. The 3p, or the p orbital, has 6 electrons, and knowing that phosphorus has it all filled up, this must be the 6 electrons representation right here. Now phosphorus only has 3 in the 2p, so you're seeing half of that. So the peak height tells you how many electrons are in those specific sublevels or orbitals. Moving on to number three. Number three, why is it not important to place numbers along the vertical axis of the photoelectron spectra of any sort? And we know that because once we know the height of one, that's an inner shell electron that's filled, and we know which orbital it is, we then can estimate what the other suborbitals would be relatively to the one that's filled. So notice how the 1s all have maintained the same height as long as they're filled. The p also would be the same height if they were filled. Of course, the valence shell would show less because at times it wouldn't be filled. So we can approximate your peak height relative to one another. So there's not they don't have to be exact. Okay. Moving on to number 4. Estimate the number of electrons at each of the 3 energy levels in neon. So if you look at the periodic table, neon starts off at 1s, then goes to 2s, and then 2p, and all of it is filled. So you can estimate the number of electrons because we know the 1s has 2 electrons, the 2s has 2 electrons, and then the 2p for neon has 6 electrons. Let's go into number 5. On number 5, what is the reasoning behind the assumption that the peak of 84.0 megajoule per mole for neon corresponds to the electrons in the n equals 1? So we're looking at n equals the 84, we know that it is the 84 megajoules is really the electrons that are located in the 1s, and the 1s is a core electron. So just by the fact that it must be closer, the 84 kilojoules must be an electron closest to the nucleus, or a core or an inner shell electron, is how we can explain that assumption that the peak must be one of the highest energy peak. For number 6, you're asked to create a PES for argon. And you're going to see me use this one little rescaling, these 2 horizontal lines that allows me to rescale. So I'm going to start off with 300. I see 300 for the 1s electrons. So I'm going to do 300 and then 200, and I'm just going to put 100 in there. And then once I go to the tens place, I then rescale it to make it 30. Here's my 30 and 20. I can even do 10 if I want to. And then I'm going to rescale it in my ones place. And so this is now 3, and then 2, and then 1. Okay. So those are my scales so that I can draw my peaks. Now the 1s, so I'm going to say electrons, E minus here. These are my representing the number of electrons, so number of electrons. Now I'm going to start creating my peaks correspondingly. Now you can label the 2 electrons that you would expect at 309. So I'm going to do 309. So it's kind of offset here. So here's where the 309 would be, and I can label it 309 here. And then my next peak is going to be 2s, and it's at 31. So it's going to be over here, slightly jetted over. And my peak is going to be the same height. So this is going to be my 31.5 peak here. And then I go to the 24, so 24 is just around here, and I'm going to make my 24, this peak here, it's going to be 3 times because there's 6 electrons. So approximately up to this height right here. This is my peak for 24.1. And then I go to 3s is going to be filled up, and so that peak is going to be at 2.8, so it's right about here. Should be the same height as the other two. If it isn't, you make sure you adjust. As I'm noticing, it's a little bit taller, so you adjust accordingly. And then for the last orbital, the 3p, it's going to be all the way filled up. So it's going to have the same height as the peak for the 24.1 here, megajoules. And so I'm going to make it at 1.5. So it's kind of jettied here. And this is the peak for that. Hopefully you can see 1.52. This is 2.83. So I label all of my peaks. There you have it. In number 7, you're identifying the elements whose simulated PES is shown below. So here you have an element's PES, and you have to identify the element from it. But it's important to note what you see in the bottom right here. This is normally not the case, but it's noted here. In the above spectrum, the peak which arises from the 1s electron has been omitted. So you're really beginning with the 2s. Honestly, I didn't realize that little note until after the fact, and when I noted it, I was like, where's the 1s electron? But here you have 2s, 2p, 3s, 3p, and it looks like there's the 3d in here. Then you see 4s and 4p. So you're looking for an element that has all of these orbitals, and it looks like it's all filled up, especially up until this last point right here, the 4p. You notice that 4p has 6 electrons for sure because of the height of this last peak. And so it must be, you look on the periodic table and you see it must be krypton. So Kr, krypton. Moving on to number 8. For the PES graph on the right, determine which element is represented and explain. So the first thing I'm going to do is I'm going to label as much as I can of the orbitals that I see for the electrons. And then I'm going to then kind of estimate it, because if we know for a fact that the 1s is completely filled, I'm going to use like a line to estimate it. And so here is the 1s. So this makes sense that the 1s is right here. And I'm going to continue that line out. Okay. Now that height is 2 electrons. And so estimated wise, if you have a measuring tool, it's even better. This is twice that. And so this is 4 electrons at this spot right here. Right here. 4 electrons. Oops, E minus. And then I know that that little bit could be debatable, so I'd say it's like 5 electrons. So it's 2p5. And the 2p5 is in fact fluorine. Now if you wanted, since it's debatable, we can also say it's neon if we want. And then if you want to also debate it to be 4 electrons at that spot, you can say it's oxygen. So in other words, this problem, because it's an estimate, we can say it can be either oxygen, fluorine, or neon, and debatable, however you want to debate it. Draw the orbital notation for the element described in PES, depending on who you pick. And I'm going to pick fluorine because I really think my estimate would be fluorine. You would then do the orbital notation, so 1s, 2s, and then 2p. Okay, so here's top 2 electrons there, 1s, 2 electrons in the 2s, and then 5 electrons in the 2p. So I'm going to singly and then double them up. So this is the orbital notation for fluorine. So my pick is fluorine for my estimate. For elements in the same group as the element above, describe the expected trend in energy value for the rightmost peak. And really, this term is wrong, so I edited in your notes, but it's supposed to be period for the same period, okay? So along the same row, for elements along the same row, describe the expected trend in the rightmost peak. So the rightmost peak is the 2p orbital, and so I would expect as you move to the right along the same period, you would expect the peak to be more towards the left. So the rightmost peak would be positioned more towards the left. Now, towards the left means there's higher energy. So there's higher energy more towards the left. And why there would be higher energy, so we're describing what's responsible, is because as you move more, as you move towards the right on the periodic table, the element has an added proton. That added proton increases the Zeph of the element, thus it's harder to remove an electron. And that's why the rightmost peak would be towards the left with higher energy. So that's my explanation for why that's the trend is what it is. Now let's go to number 9. Identify the elements whose PS is on the right. Why is one peak higher than the others? And we can answer B pretty quickly. It's all about the electrons and how many electrons are in those orbitals. So the first thing I want to do is I kind of want to estimate. This looks like it's the 1s. I always start off with 1s. And then this is my 2s, 2p, and then 3s. And from the height of what you see here, the 1s is completely filled with 2 electrons for sure. So my reference is that peak height represents the 2 electrons. This peak height right here. This is another 2 electrons. This is 6 electrons all filled up. So an element that has filled up 1s, 2s, 2p. Now the 3s doesn't look as tall as the 2s here nor the 1s here. So it looks like it's only 1 electron. So I'm assuming it must be an element that has 1 electron in the 3s, and that is sodium. So it must be Na. Sodium. Why is one peak larger than the others? Well, that's because the electrons that are housing in those orbitals or suborbitals, and so you're seeing higher peaks depending on how many electrons are in those orbitals, suborbitals. In which sublevel are the electrons represented by peak A? So it's the 3s, and it's 1 electron that's in the 3s in the end. But that's not what the question. So it's the 3s. That's all we need. All right. Now it's your turn. Your turn to go over and practice FRQ number 3. Once again, this is you to practice your ability to read this PES chart and what it entails, and then of course check your answers with the answer key below. So we're entering into Coulombs Law and periodic trends. So let's look at Coulombs Law. This is an equation that you will never have to use per se. You will apply them. So you're looking at charge as it relates to force, Coulombic force, and then distance as it relates. Charge is directly proportional. Distance is inversely or indirectly proportional. So charge Oftentimes we use Zeph as our go-to evidence for charge, and then distance is the energy levels, which is letter N. That's how we know energy levels. We use the letter N. That tells you how many shells or energy level there are in an atom. And then charge is the Zeph is effective nuclear charge. It's basically uh, the positive nuclear core's attraction, or in other words, the proton's attraction on the valence electrons in an atom. As you go from left to right along the period, the number of proton increases, which increases the effective nuclear charge, the Zeph, causing the protons to pull on the electrons while on the same energy level, and the same energy level, which is N. Thus, the force increases. So Coulombs Law states that as that happens, the charge increasing, the force must also increase proportionally. Core charge is quantified, and it's quantified using Zeph. This is a quantitative way for us to be able to understand how charge affects force. So please make sure you understand that all you're doing is counting the number of protons and subtracting the inner shell electrons. So let's go ahead and calculate Zeph for these elements across the period. As we calculate, here's an example. Lithium, you've got 3 protons, and lithium has 2 inner shell electrons. And so you add those two, it will subtract the inner shell electrons from the protons, and you get a positive 1 Zeph. You don't need the positive there or negative, you just need to make sure you follow this equation here. Let's move on to beryllium. Beryllium has 4 protons, minus the inner shell would be all the electrons in the first energy level, which are 2. So beryllium Zeph is 2. Boron, moving over to the next element, has 5 valence electrons, or protons, and 2 inner shell electrons, so the Zeph is 3. Carbon has 6 protons, 2 inner shell, so its Zeph is 4. So now what you notice is the Zeph is increasing as you go across the period 2 here. And so it goes from lithium plus 1, beryllium 2, 3, and then 4, all the way to 4. So the Zeph is increasing because the core charge is increasing. Core charge is the number of protons. Notice the protons are increasing as you go from left to right. So let's compare 2 ions, sodium ion and fluoride ion. And we'll notice the common ions are both isoelectronic with one another, which is truly isoelectronic with neons. So you're seeing neons. Both elements have the same number of electrons as neon. And with that, what differs is the core charge. Sodium has a different number of core protons, 11, versus fluorine, which has 9 protons. Sodium is going to have a stronger core charge. With a stronger core charge and a Zeph of 9, you're going to see sodium to have a smaller ionic radii than fluoride as a result, because sodium is going to pull onto its electrons much more, decreasing and condensing the ionic size to be smaller than fluorine, which has a weaker core charge of a Zeph of plus 4. Group trend. As you go down the group, the principal quantum number or energy level increases, which increases the distance, while the Zeph stays the same for the atoms in the same group. Thus, force decreases. So Coulombs Law states that as you increase in distance, force decreases. And you'll notice, as you see here, hydrogen has N equals 1. Then comes lithium, which has an N equals 2, and then sodium, which has N equals 3. Now, as you increase in size here, notice the nucleus is further from the valence shell here. Nucleus is closer here and even closer here. So because the nucleus is closer, you're going to see that hydrogen holds on to its valence electrons a lot tighter than sodium here, because because sodium's valence electrons are further from its nucleus, which is where the positive charge is located. So with that, you can explain using core charge. In calculating the Zeph, just as a side note, we're going to see how Zeph changes going down a group by calculating that. So let's do the Zeph of hydrogen. I'm going to do the Zeph calculation for hydrogen first. And hydrogen has 1 proton minus 0 inner shell, so its Zeph is 1. The Zeph for lithium starts off with 3 protons and 2 inner shell electrons on the first energy level, so it has a Zeph of 1. And then the Zeph for sodium. Sodium has 11 protons, and sodium has 10 inner shell electrons. Those 10 come from the 1s as well as the 2s and the 2p. So that's totaling 10 electrons. And that gives you 1. So notice how the Zeph stays pretty much the same for elements in the same group. Let's go ahead and answer these example questions with respect to Coulombs Law and periodic trends. For the first question, arrange the following elements or atoms in order of increasing ionization. You're going from low to high. So the first thing I want to do is figure out where they're positioned. These elements are positioned on the periodic table. In other words, I'm going to record their N. Strontium is on the 5th energy level. So I'm going to put 5 above strontium. Cesium is located on the 6th energy level. By the way, there should be a comma here. Sulfur is on the 3rd energy level. Fluorine is on the 2nd energy level. And arsenic is on the 4th energy level. So you can actually go least to greatest just by strictly the energy levels, because they're all located on different energy levels. So the answer is, starting off with the weakest, the largest atom will have the lowest ionization energy, because the largest atom will have its valence electron furthest from the nucleus, and thus, being that the distance is farther away from the nucleus, the Coulombic force is going to be weakest, which means less energy is needed to remove an electron. So I'm going to go from big to small size-wise. Starting off with the biggest is cesium. So cesium will go first. Then comes strontium. Next is arsenic, sulfur, and last fluorine. So this is increasing ionization. You're seeing higher ionization energy here and low ionization energy at the beginning. So it's increasing in ionization energy. Now we're going to number 2. The family within a period, any period with the greatest negative electron affinity is usually going to be the halogens, because the halogens, the greatest negative electron affinity means the substance or the atom likes to gain an electron, and upon gaining an electron so easily, it releases a lot of energy. So it's in a better potential state when that atom gains an electron. And those that are easily gained are the ones that have the greatest change in energy. And again, halogens, because halogens are they have a high amount of Zeph, and that high Zeph, that high strong core charge, allows them to easily gain an electron to fill up its valence shell. And will the electronegativity of barium or strontium, or barium, be larger or smaller than strontium? So barium's energy is on energy level number, notice I'm going right to the energy level first and foremost. And then strontium's energy level is on energy level number 5. with that, barium is going to be less electronegative than strontium because barium's valence electrons or outer valence shell is further from the nucleus, so its attraction for electrons is lower, and the answer is smaller. And that is a force to distance relationship, inverse relationship, that is. Compare the electronegativity of tellurium to that of antimony. If you notice, tellurium is on energy level number 5. Just double checking. N equals 5. Antimony is right next door to tellurium. Its element symbol is Sb, and it's also energy level 5. So you really do have to calculate the Zeph. The Zeph calculations for both tellurium and the Zeph calculation for antimony. And tellurium has 52 protons. And counting the 4D, filled 4D, which is on the 4th energy level, it has 46 inner shell electrons. So the Zeph is 6. Antimony has 51 protons and 46 inner shell electrons. So antimony Zeph is 5. Now, strictly with Zeph, the one that has a higher Zeph will have a stronger positive core charge, and thus it will have a stronger force of attraction for another atom's valence electrons in bonding. So tellurium will have a higher electronegativity than antimony. And I'm going to abbreviate electronegativity. Than antimony, and that's because of the Zeph is stronger. The core charge is stronger. Now we go to number 5. We're looking at arranging the following by increasing size, and so we notice that all of these are isoelectronic ions, which means they all have the same number of electrons as argon. And so we're really going to have to look at the protons as a way to delineate one ion from the other or one atom from the other. And by increasing size, the more protons you have, the less smaller you are. And so we're going to go from more proton, which is larger or smaller in size, and then to less protons, which increases the size. So calcium ion will go first. Calcium ion only has has a lot of protons, which is 20 protons. Then comes potassium ions, trailing with 19. Then comes argon with 18. Chloride ion with 17 protons. And then sulfide ion with 18. And sulfide ion having less protons will have a less attractive or less Coulombic attractive force to its valence electron, leading to its smaller size. Now we go to the next one, number 6A. You lose electrons, you get smaller. You gain electrons, you get larger. So as we go through each of these, as you compare the element, the neutral element, with its ion, you're looking to see if it lost or gained an electron. 2 plus means it lost 2 electrons. So it looks like the larger species is the neutral atom. Here we have F and F minus. F minus is larger because it gained an electron. Now we go to sodium and potassium. They're different elements. Sodium has N equals 3. Potassium is on N equals 4. So the larger species definitely is the 4th energy level, which is potassium. Let's look at the next set of problems. Now, level 1 means it's just really tell me what it is. Now level 2 comes to a higher level of thinking where you're explaining and telling me what it is, but also explaining with some reasoning and evidence. So in number 7, consider Read the question. Consider the ionization energy of R and S shown below. R and S are in the same period on the periodic table and are adjacent to one another. In which group would one find element R? So let's look at R's data. Looking at R's ionization energy, the first, second, all the way to the ninth ionization energy, what I'm looking for is the highest jump in ionization energy, meaning the difference between each successive ionization energy. I'm looking for the biggest difference. And to me, where I see the biggest difference would be right here between the 7th and the 8th. Notice a huge gap between the two. 17,000 approximately, or 17,868 going to 92,038. This is a huge gap. Now, that huge gap means that the R has 7 valence electrons, and the 8th one is when you go into the core, the inner shell. So this is whatever R must be, R must have 7 valence electron. Now, going to S. Well, since I know it didn't ask for S, but I'm suspecting it will eventually. And so looking at S, I comb through and see where there's a huge jump in energy. Oop, I see it right here between these two. And so it looks like whoever S is, it must have 8 valence electrons, and that completely makes sense because R and S are next door to each other. And so R and S one must be a halogen, and then one must be a noble gas. So again, I'm looking for the biggest gap. Anything before that gap are the valence electrons being removed, and then the gap is occurring because you're moving into a core electron, an inner shell electron. Fortunately, we found that element R has 7 valence electron, and we knew it was a halogen. S must be a noble gas of some sort, so we know that R must be on the will lie to the left of element S on the periodic table, and you can explain it using the number of valence electrons and what group of elements they must be, meaning halogens versus the noble gas. Going on to letter C, which is the first period on the periodic that these elements could be in. So if it's on the first period, that means it has to be where you see a halogen and a noble gas. So it must be the second period. That's the first time you ever see this occurring. It must be on the second, possibly second. The first time you'll see it is the second, and then it moves on to the third. And you can explain it because the second period has halogens with 7 valence electrons and noble gas for the first time. That's the first period you'll see after the first. The second period is where you will see the first noble gas and also a halogen. So both exist. So they have 8 valence electrons. Why are the second ionization energies of both elements larger than their respective first? Because ionization energy is calculated by taking however much energy for that removal of that electron plus the previous first electron or previous electrons that are removed. And so it's a summative value. And that means that value is always increasing, and due to you're adding energy from the removal of another electron. So you're really adding it as you go kind of thing, summated value. It is found that S has the largest first ionization energy in the period that it is found. What does that tell us about S? It tells us that S must be located somewhere on the right side of that period, and it must be a noble gas because it has the largest first ionization in that period. So S must be a noble gas. Um, and noble gases have a hard time losing an electron because it has a full shell with a stable configuration. It is found that element Q, which is in the same period as R and S, which lies to the left of the element R in the periodic table, only has values for the first 4 ionization energy. Suggests a reason for this observation. Oh, it must be Q must be beryllium. So is found, it's the same period as R, but lies to the left. Okay, so beryllium, Q must be Be. Um, and it only has, and Be only has 4 electrons in total. So that's why it only has the first 4 ionization energies. You can't remove any more than what it has. Write an equation to show the second ionization of calcium. So if calcium loses, so plus IE1, I'm going to call it IE1. When it loses an electron, it produces a +1 charge and, of course, 1 electron loss. Its second ionization is going to look like this. Ca2 plus IE number 2, forming Ca2 plus and another electron. So that's you are really writing this equation right here. But it helps to write the first ionization energy to see what is the product of it, which is calcium +1. In which group does A appear on the periodic table? Once again, I'm looking for the biggest gap, and the biggest gap occurs between the third and fourth. So I'm thinking the element must be an element that has 3 valence electrons. So it must be boron family, which is group number on the periodic table, group 13. Predict the formula of compound A with fluorine. So it'd be BF, or sorry, so instead of B, I'd say A, so it's AF3. Because it has 3 valence electrons. What is the minimum number of electrons that A must have? We said it would be 3 valence electrons. Let's hop over to number 9. Number 9 says to write the first ionization energy of atomic fluorine. So atomic fluorine would be neutral fluorine, and then I'm going to add 1681.0 kilojoules per mole leading to, and upon adding that energy, fluorine becomes F plus 1 because it lost an electron. So an electron is released. Now we're going to do the second ionization energy, but we're not given that second electron, or sorry, the energy to remove that electron. So I'm going to call it IE2. Applied to F plus 1, which is the ion that created from the loss of an electron. And then, of course, Fe2 plus 1 electron release. Now we get to level 3 questions. Level 3 questions are really rich question or responses where you're really giving some depth to your answers. Aside from just telling me what it is, you're actually giving me some evidence and reasoning. I'm going to verbally go through the work for this. I'm going to write some things down, but verbally go through the rationale and evidence, and probably write down the evidence as well. But the explanation part will be verbal. Sodium has a lower first ionization energy than lithium. So the first thing I'm going to do is set myself up with energy levels. Sodium is on the third energy level. Lithium is on the second energy level. So to explain this comment, this statement, this claim that's being made, sodium has a lower first ionization than lithium. We can explain it by saying that the energy levels, or sodium's valence electron, is further away from the nucleus than lithium's. And because sodium's valence electron is further away, to remove that valence electron requires less energy because there's less force acted on that valence electron, less Coulombic force. And that would explain why sodium has a lower first ionization. Removing the electron from a further sodium is going to be easier than removing an electron from lithium, because sodium's electrons, valence electrons specifically, is going to be further from the nucleus, and thus there's less force holding on to that electron. Now we go to carbon, and has a lower first ionization energy than oxygen. Okay, so we're going to go into Zeph because they both have the same energy level. So oxygen and carbon are on the second energy level. So the Zeph calculation. So the Zeph of carbon is calculated by taking the number of protons, 6, minus the inner shells, which is 2, so the Zeph is 4. The Zeph for oxygen is 8 minus 2, which is 6. So obviously oxygen has a stronger core charge because it has a Zeph of 6 versus carbon, which has a Zeph of 4. And with that means carbon is going to have a lower first ionization energy because carbon has a weaker hold on its valence electron, and that's because carbon has a weaker core charge, less protons inside the nucleus than oxygen. So removing an electron is going to be easier for carbon than it is for oxygen. Moving on to the next. Consider the ionization energy plot below. Explain each of the following. There's an increase in ionization energy from sodium to argon. Now, sodium has atomic number 11, so this is sodium right here. And then argon is 18, so this is argon, right? Oops, 8. Argon. Erase that. Let's label it argon. So it looks like the trend is there's an increase. Explain the trend. And we know that Zeph is increasing going across the period. The nuclear charge is getting stronger and stronger and stronger. Thus, removing an electron is going to be more and more difficult across that period as the core charge is getting stronger. The force is getting stronger on those valence electrons. Thus, removing an electron is going to be harder for argon than it is for sodium. Now we go to B, letter B. The first ionization energy of neon is significantly higher than argon, but significantly lower than the first ionization of helium, despite all the elements are in the same group. So let's kind of explore each of those elements. Helium, neon is on the second energy level. Argon is on the third energy level, and then helium is on the first energy level. So the first ionization energy for neon is going to be definitely higher than argon because argon's valence electrons are farther from the nucleus. Farther distance means weaker Coulombic attraction, so argon is going to have it's easier to remove an electron from argon than neon because neon has a stronger core, its valence electrons are closer to the nucleus, so the Coulombic force is stronger. But significantly lower than helium. So helium will actually have the highest first ionization energy because it has no inner shell electrons, and so there's essentially just the nucleus and the valence electrons. So the distance is going to be even closer without any other shell interrupting between helium's nuclear charge and its valence electron. So helium is going to even have a larger first ionization energy because helium's valence electron is closer to the Coulombic force of the core charge, or the protons inside the nucleus. Helium has let's go to the next question. Helium has the highest first ionization of all the elements. Well, that's certainly because helium's valence electron is closest to the nucleus, and it has nothing shielding the attractive force between the nucleus and the valence electrons. And so helium definitely would have the highest ionization energy. And recall that helium's first, all its electrons are completely filling that first energy level. First energy level only takes 2 electrons. So removing an electron from helium is going to be even harder due to helium having a pretty high Zeph and very strong core charge and less energy levels or no energy levels other than the first energy level that it has. Now it is your turn to work through these questions. This is all the FRQs. Go ahead and work through each one by one, making sure you thoroughly explain this FRQ. So go ahead and go through FRQ number 5. When you get to D is really a question that goes into the next unit on bonding and intermolecular forces. But I would look it up and kind of look up why chlorine has a lower boiling point than bromine. It is not this particular unit, it is the next unit. All right, let's go into mass spectroscopy. So this is also a new AP topic for us. And in this topic, we're looking at mass spectroscopy and how we've collected data using mass spectroscopy, specifically data to help us define what is called the average atomic mass of an atom. What we have to do is we have to take these to find the average atomic mass of an atom, we take all the naturally occurring isotopes that exist and the percent abundance of each type, and then we calculate the average based on what is called a weighted average. We use this lovely equation right here. Average mass unit is calculated by taking the sum of the mass of each isotope multiplied by the relative abundance. And then, so we do it for each isotope and we add them all together using thus the summation symbol. Let's now calculate bromine's average atomic mass. Now it says oxygen here. It's a little error. It should be fixed on your notes, but it should be bromine. Okay, and it has two naturally occurring isotopes. So let's go ahead and look at the calculation for bromine and bromine's average atomic mass. So the first isotope that we see here is bromine 79, and its exact mass is 78.92. Notice it rounds to 79 pretty nicely when you round it to a whole number. Likewise here, this rounds to 81, but if you're given an exact mass, you use the exact mass. If you're given the rounded mass number, then you use the rounded mass number, and only that. So to be more precise, given the exact mass, you use the exact mass. Otherwise, use the other mass number. So the percentages are all going to be turned into decimal form, and that way we can multiply our percentage, our isotope mass times our percent abundance. So multiplying these two values, I get, for the first value, 40.09. For the second one, I get 39.81. Now, these are all rounded numbers that I'm writing down. I'm not going to round until the very end. So upon adding these two numbers together, I get 79.90. AMU, atomic mass unit, is what that means. And so if you look in the periodic table, you'll notice fine bromine, and you'll notice that its molar mass, or in this case, its atomic mass unit, is 79.90. That's the technical name of that number on the bottom of each element symbol. Its atomic mass unit. So how do we know these isotopes existed in the first place? Well, Dalton actually, without the technology, made some really important proposals in the atomic theory. He had 5 statements, one of which was atoms of the same element are identical. Today we know that that's not true because of the existence of isotopes, and the isotopes have different masses with them because they have different subatomic particles, specifically neutrons. So mass spectroscopy was a technique that we used to study these isotopes. It's used to both count and weigh atoms in a sample to yield the data table similar to the one we calculated above for the isotopes of bromine. Go ahead and click on this website and watch this video about mass spectrophotometer, and we'll revisit after you finish watching. Now, we calculated earlier the average atomic mass of bromine, and we saw that there were 2 isotopes. There was bromine 79, and then there's also bromine 81. Now, if you look at the spectrophotometer or the spectrum for bromine, you'll notice that there is actually 2 peaks at those 2 spots. Bromine 79 as well as bromine 81. So those are your 2 peaks that represents the 2 isotopes that we just mentioned. So there's bromine, and I'm going to use the hyphen symbol, 79, and there's bromine 81. Now, what do you think the peak for what is represented by the peaks around 160? So this 160 peak is kind of a little odd, but if you think about the number 160, it must be twice one of these 2 numbers, or in between these numbers, which is what the average ended up being. The average was 79.90, and so I'm thinking to myself, it must be some kind of diatomic bromine of some sort, and it might be one of those that was created as a result of the interactions between the isotopes combined, that is. Let's label very clearly what each of these peaks would represent. So this first one is lower than 80, so it's bromine 79. And I'm going to put a plus because it ionized, okay? For it to be recorded it had to be ionized into that cation. So this is bromine 81. So, and I'm going to put it over here as well. I forgot to do that. So this peak is 180, and we knew that it was all diatomic, but what combinations of these isotopes could make these diatomic molecules, or these diatomic ionized molecules? Okay, so the first one is, it looks like it's 158. So what could be causing the 158 in the end? And I'd say it's bromine 2 plus 158. And the reason why it's 158 is because it's two of the 79 isotopes combining together, colliding together and combining. And that will give you 158. So this high peak right here is bromine diatomic molecule with an ion charge, and it's 160. It's right on 160, and that must be a combination of 79 plus 81. You'll notice that will give you 160. The last one is bromine 1 plus. And it is 162. And so why it's 162 is through the combination of two 81s. So 81 plus 81 is 162. So that explains this question right here, number 3. Now, what we're going to do, this is like another POGL, where you're going to go through this, and I will show, the answers are at the very end. So hopefully you've had the chance to watch this video. You've got to watch this video. That way you can understand what this model shows and what is going on. I would like for you to go through and run through this POGL by yourself or in your groups. I might have this done as a group activity in our class Zoom sessions or our class sessions. Continue to answer the questions, moving into the next page, and then finish it up. There will be some Ngo check. Ngo check means I will be there to check to make sure you're doing it well and you understand it. And so we'll ask some previous questions to make sure you're good to go. And here's the last Ngo check, and that ends the POGL. Now going into, you'll see there's an FRQ that's dealing with mass spectrophotometer, and a couple of them, I think. FRQ 7, 8, and 9 will be homework, and 10 on mass spectrophotometer. And that ends the unit on periodicity and trends on the periodic table.